Okay, so last time I talked about, so we're going to talk about the topology of the space from last time. Okay, so we had the space, all right, so the space of, okay, so I remember lattice in Rn was just this thing, which is a linear combination of basis vectors. Now I want to talk about the space of lattices, so let's call this the space of all possible lattices, all lattices in Rn. And as before, we're going to normalize them to have, let's normalize them to have density 1. So that means the determinant, if you form these guys into a matrix, is 1. Okay. So the goal of today, we're going to talk about the topology of the space, in particular the Betti numbers. And the main goal of today, actually, I'll just get to a point where it's clear that there's something, I just want to get to a point where it's to say there's something interesting about this that requires some explanation, and then we'll talk about the explanation next time. Okay, so most of it is actually just talking about how people analyze this type of question. Okay, now one thing we'll do is I'll work not with this space, but the space of lattices. You can quotient by rotation. Okay, as far as all the eventual things I'll talk about, it doesn't really make a difference, but it makes things a bit cleaner. So we'll do that. So let me. The space is often written in a different way as a quotient. So I'll describe that. If you one way to sort of put coordinates on the space, lattices modulo rotation, is you record not these lattice vectors, but you record their inner products. Okay, so then if you do that, this is now invariant under rotation, and that identifies this space, lattices modulo rotation, with the space. Okay, so when you do this inner product thing, you get a symmetric n by n matrix of determinant 1, and I guess it's also positive definite. But you have to account for the fact that a lattice has many different bases. Okay, so you get this space quotiented by the action of SLNZ, which means n by n integral matrices of determinant 1. And the action here is if you have an element in SLNZ and it acts on a symmetric matrix, in the usual way that you act on a quadratic form, gamma transpose A gamma. Okay, so the kind of thing we know about this, for example, I won't actually talk about the proof of this, but just to give you some, here's something we know about it, that the sum of the Betti numbers of this space, Ln, if you add up all the Betti numbers, it's very large. Okay, so if you take this set grows at some rate, which is like it's exponential, again in some constant n squared log n. So the space is especially when n is large, it's topologically very complicated. Yeah, I won't explain this, but we'll see how, kind of explain how the way people analyze it. Okay, are there any questions? All right, this Ln is what I'm going to do is this Ln fits inside a larger class of spaces, which are called the arithmetic locally symmetric space. And in fact, everything we say about the topology of this Ln applies to all of these spaces. And it's going to be helpful for me to describe this, because that way I can sort of talk about simpler. This has a larger supply of toy models. Okay, so even if we're strictly interested in this question, it's helpful to think about this larger class. So I'll describe to you what these are. Before I do that, let me just make a comment about this. this guy here, let's call this Sn. Okay, so Sn is going to be this symmetric n by n matrices of determinant 1 that are positive definite. This space, this Sn has a Riemannian, that's kind of a natural Riemannian metric on it, which is invariant by the action of SLNZ. Okay, and in particular, that means that this ln has 1, 2, gets a metric. And what this what the metric is, if I write it in just the formula for the metric is given by, if A is a symmetric matrix, you can write down this expression, trace of A inverse dA squared. This is not very informative. The way you measure the distance between two symmetric matrices is you simultaneously diagonalize them, and then you essentially measure the L2 distance between their diagonals after you take logarithms. Okay, so there's some very nice formula like that for the actual distance in this metric. Anyway, the important thing is this metric is invariant, so it gives this space a natural Riemannian metric. So these arithmetic locally symmetric spaces, whatever they are, they'll be some special class of Riemannian manifolds. And this Riemannian metric, this Riemannian structure is extremely useful. All right, even if we're just concerned with this topologically, because it'll enable us to do some kind of Hodge theory on this space. All right. So I'll tell you first. There are two ways you can kind of think about these things. One, I'll just tell you the definition, which comes from number theory. But they also have some sort of special place inside the world of Riemannian manifolds. So I'll start with the number theoretic definition, then we'll come to the other thing. So, okay, first I have to tell you what an arithmetic group is. So I'm just going to I'll give you a slightly informal definition. So an arithmetic group, this is meant to be some generalization of SLNZ. Maybe I should have written what SLNZ is just to be clear. So SLNZ is just an n by n matrices, integral matrices with determinant 1. Okay. So an arithmetic group, the informal definition is just the integral points of a matrix group. So the integer point, let's say, how do you say integer point. So let me give you some examples. SLNZ, because these are n by n integral matrices with determinant 1, or you can take any of the classical Lie groups and you just impose the condition that all the entries are integral. Okay, so SO. Okay, so the elements of the corresponding Lie group were all with the integral entries. A slightly more complicated example is something like SL2 of z square root 2. Okay, so the definition of this thing is that it's all the 2 by 2 matrices with entries in this ring z square root 2 and determinant 1. Something like this, and determinant 1, which it involves the square root 2, but the thing is you can think of it as being the integer valued points of some group of 4 by 4 matrices. Okay, you can kind of encode this by some group of sort of 4 by 4 group of integer matrices. So there are many things which fall I've said this slightly informally, but there are many things which fall in this description which don't immediately look like this. For the purpose of this talk, you can just think, for example, about SLNZ or symplectic matrices with integer entries. Okay, so I'll use the letter gamma for any of these things. Okay, this has some I mean, there's a precise definition of this, but you don't want to hear it, and I don't want to give it. So it's, if you do want to hear it, you can ask me. But I think it's better you just think about these examples. OK, now the thing is, each one of these things, each such gamma, has associated to it a kind of canonical Riemannian geometry. Each such gamma acts on some sort of canonically determined complete Riemannian manifold, which I'll call S sub gamma. And this is actually a Riemannian symmetric space, which means that it has some which means that geodesic reversal around every point is an isometry. So this thing has a lot of, so this acts isometrically on this. So let me give you again in the case of SLNZ, the associated space is this symmetric n by n matrices with the metric that I described over there. For SP2NZ, this thing is something called the Siegel upper half space. And this thing, it looks like a little bit like the upper half plane, except you use matrices instead of complex numbers, and the notion of one coordinate being positive is replaced by positive definite. This example here, SL2 z square root 2, let me talk about this one in a bit more care. The symmetric space is the product of two copies of the upper half plane. So let me talk through that one a little bit more. So upper half plane means those things in the complex numbers with positive imaginary part. This thing has is usually equipped with this metric of constant curvature minus 1, which is given like this. And the action here, let me also write the action. So if you have a matrix, so if I have some matrix, this thing belongs to SLT to z squared 2, and you want to act on a pair of things, z1 comma z2, it acts by fractional linear transformations. So alpha z1 plus beta over gamma z1 plus delta. And then it does the same thing in the second coordinate, except you conjugate all the entries. And conjugate means that you switch the sign of square root 2. OK, now the details of this are not important. I'm just writing it to say that I didn't explain how you get this. But every arithmetic group, when properly defined, it comes along with a canonical Riemannian geometry on which it acts, okay, which generalizes the relationship between SL and Z and these symmetric matrices. And this is very useful for us because it gives us some geometry with which we can understand this group. All right, and then the definition of let me give you one last example before we go on. If you took SL2 over the Gaussian integers, this example was considered by Bianchi in the 19th century. The corresponding space it acts on is the hyperbolic 3 space. Okay, so the R3 with the third coordinate positive, and the metric looks just like this. Okay, so I haven't told you how it acts, but it acts in a way that preserves that metric. And so for each one of these, you can kind of make a generalization. So this arithmetic locally, what this means will be a Riemannian manifold of the form S gamma quotient by gamma for some arithmetic group gamma.
So can you explain minus gamma?
Yeah, okay. So every arithmetic group sits in a, I didn't say the definition, but it's part of some matrix. It's essentially the integer points of some matrix group. Okay. So it sits inside a real Lie group, which you get by taking the real points of that. The S gamma is the symmetric space associated to this, which means it's the quotient of this by a maximal compact subgroup. And that carries essentially a unique metric that's invariant by this G of R. Okay, so for one way I could have, maybe I'll just, yeah, thanks for the. So in this case here, this Sn, you can identify it with a quotient of SLN R by its maximal compact subgroup, which happens to be SON. And similarly here, the S gamma in this case is SP2NR modulo its maximal compact subgroup, which happens to be the unitary group, and so on. Is that okay? Yeah. Yeah, the other thing maybe I should say is these metrics, they're of, the curvature is less than, sectional curvature is everywhere less than or equal to 0. Okay, we're not really going to use that, but just in terms of having a picture of what this looks like. Yeah, any other questions? Don, you look unhappy.
Well, this formula here, is that Sn there just for the symmetric n by n matrices?
S, yeah.
Why is there a gamma attached to the thing if you haven't divided by gamma? See, S gamma, you've written S gamma as SP2NR modulo maximal compact. I would prefer you put a gamma on the left there.
Where?
You want to divide by gamma to make your symmetric.
Well, okay, how about, I'm going to call this X gamma. Let's call this X gamma, okay? So to gamma, I'm saying there's a canonically attached. It's true that there are many different gammas.
Yeah, without division. So there, as written on the board now, that formula is not.
Yeah, he said it was just.
So you add
Okay.
it later.
Okay, yeah, this thing was Sn, and then this same thing mod SLN Z. That's the space which was this Ln. Sorry. Yeah. Any other questions?
You don't really literally need it to be the integral points of the gamma, right? I mean,
No. Okay. Well, but I think this, said. I think if I say that an arithmetic group is like the integral points of an integral model of a semi-simple group, I think that's pretty close to the, because you can have lots of integral models, right? So I think it's said carefully, that definition is pretty close to the true one. Okay, now, so this is some class of manifolds, of which this is an example. Now, the other way to think about this, which will be very, so for example, in this class of manifolds, there are many hyperbolic 3 manifolds, which for if you take any subgroup of this, so you take z of square root minus 3 or something, this S gamma remains H3, so you get all these hyperbolic 3 manifolds. In fact, these have some role in Riemannian geometry. So, I mean, there are, okay. So if I have let's say I have a general Riemannian manifold. It has a holonomy group. So I'll just say what this is. So what you do, so at the moment this is a general Riemannian manifold. Okay, I want to say how these are, how these stand out in the class of all Riemannian manifolds. So you take a point on your Riemannian manifold, and then you go around some loop, and you watch what happens as you parallel transport around the loop. Okay, and so when you get back to where you started, stuff has spun around in some way, so you get an automorphism of the tangent space by going around that loop. And if you look at all the different loops, you get a subgroup of the automorphism group of the tangent space. Okay, so this is called the holonomy group. And for a generic Riemannian manifold, this is equal to, this holonomy group will be, you'll get every possible rotation. So you'll get all the automorphisms of this tangent space which preserve the Riemannian form. Okay. However, there's a finite, there's a theorem of Berger from the 1950s, where he classified all the possibilities for the holonomy. Okay, it's kind of amazing you can do it, but he classified them. For example, so there are just a small number of cases in the list. For example, the first case is that the holonomy could be, or it could be, instead of this, it could be a unitary group. Okay, unitary group in the same number of variables. And in this case, this corresponds to M being a Kähler manifold. It's exactly. So I'll remind you what a Kähler manifold is in just 1 second. So there's a short list of possibilities, and one of the lines in that list is that M. So I'm not going to say all that. There's a few other lines, but sort of one of the lines in the list is that M is a quotient of a symmetric space, and in particular so this includes all these arithmetic locally symmetric, these examples that I said. And in fact, these are in some sense a very large part of this line. Okay, so in the class of Riemannian manifolds, these are distinguished by the fact that the holonomy is very small, okay, compared to what it could be. The actual point about saying that, though, is that a very good sort of metaphor for how to think about this is it's some kind of analog of a Kähler manifold, but with sort of even more stringent conditions than the Kähler one. Okay, so the moral of this is that these anyway. Okay, so this is a useful metaphor to keep in mind, and that's what we're gonna.
Is that the most special class in this?
It's the in the sense of having small holonomy. Yeah, in some sense, like the holonomy groups look much smaller. For example, for this one here, the tangent space here is symmetric matrices of trace 0 or something like that. And the automorphisms you get are the holonomy is all the things of the form, all the transformations of the form A goes to O transpose A O, where O is in SON. Right, the full automorphism group here is something like it's quartic in N, but the actual holonomy is only quadratic in N. So when N is large, the holonomy group is extremely small compared to. All right. Question?
Defining a locally symmetric space as a quotient of a symmetric space, is that what we're saying?
So that's a larger class. I'm defining it as the class which arises from arithmetic groups. So that is a subset. If you're just looking, for example, at the compact examples of this, it's a pretty large subset of that. It's probably the most interesting subset of that class. Yeah, so I don't mean to say this is exactly the same as this, but this is a very large piece of that. Right, so the reason, so in particular, we can try to adapt, we can adapt ideas from the Kähler case. Okay. And in the way that people study the topology of this space or any other of these arithmetic of these guys is exactly by kind of adapting Hodge theory. All right, so now I'm going to talk a little bit about Hodge theory. So I'm going to recall what Hodge theory says for Kähler manifolds, and then I'll adapt it to this class of spaces. Hodge theory. Are there any questions? Okay, so M is going to be a compact Kähler manifold. Oh, and here I should have said, okay, here's something I should have said. These guys here, they are not always compact. Okay, for example, this Ln is not compact. Okay, but it's almost compact. They always has finite volume. All right, it's a Riemannian manifold, so you can measure its volume, and that volume is always finite. All right, so it has maybe some piece going to infinity, but that piece has small volume. In the rest of the talk, I'm going to be sloppy about this point. I think you can effectively pretend for the purposes of talk that these spaces are all compact. Okay, it's a bit of a lie, but for for our purposes. Many of them are, so let me say, has finite volume and is often compact. Many of them are compact. And let's not worry about it for now. Okay, so now suppose you have a compact Kähler manifold. So what this means is, it means it's, well, let's start off by, we'll add words one by one. Okay, so start off with a compact manifold. Okay, if you have, then it has some, if you have a closed differential form on it, it gives you a cohomology class. All right, because you have this form, and then you're allowed to integrate it over cycles. So that's the and being closed means that it satisfies the right boundary conditions to be a cohomology class. Okay. Now this this map is surjective but not injective. There are lots and lots of differential forms that give you exactly the same cohomology class. But if you add the word Riemannian here, that improves the situation because you can choose, in the Riemannian case, you can choose for each thing here a representative of minimal norm. Okay, so you have a minimal norm representative, and these guys, this defines some, it actually defines a subspace, which I'll call Hj. These are also called harmonic forms. And these now represent, they uniquely, each cohomology class has a unique harmonic representative. Okay. Now we'll go to add some further structure, which is you suppose the manifold is Kähler. And what that means is that let's suppose that M is Kähler. And what that means is it has a complex, every tangent space has a complex structure that's compatible with the Riemannian structure. Okay, so the compatible is a little bit stronger than you might think, but I won't say exact. It's fairly reasonable. So complex structure that's compatible with the Riemannian structure, and I haven't said. Okay, so you have to define compatible rightly, but let's just assume there's a reasonable way of saying it. All right, in that case, so now suppose that, so in addition to what we had over there, I'm going to add in a complex structure, and I'll see what more I can say. Are there any questions? Okay, complex structure means that every tangent space, you can act by complex scalars on it. Okay, and I'm going to just look at inside these. I'm going to look at rotations. Okay, so just complex numbers of absolute value 1. If you have a complex vector space, I can rotate vectors, so to speak, using the fact it's a complex vector space. Okay, so this circle, if I can rotate tangent vectors, I can also rotate differential forms. Okay, so it acts on J forms on M, just because at every point you can J forms are defined functorially from the tangent space. So if you have an action here, you get an action here. Now comes a fact which is no longer trivial, this so far as formal, which is that this S1 action actually preserves the harmonic forms. Okay, so this requires you to actually compute locally. This preserves this harmonic forms. Okay, I mean, the way I've said it, it's not even clear it preserves a form being closed. Okay, so you have to check something. This is not formal, and it uses the exact meaning of this word compatible. Okay, so what we get from this is this S1 also acts on the the homology, yeah, so if you get an action of S1 on this side, and so there's action of the circle on this one, and so, for example, if you look at how -1 acts, -1 here, just to give some examples, -1 acts by negating vectors everywhere, so it acts by -1 to the j. Okay, so this is actually a very strong thing, but let me just draw a simple consequence just to show you it has some content. Right, if you just think about elementary things about representation of the circle group, this is enough to tell you that the dimension of these cohomology groups is even when j is odd.
-1 even j is 0.
What? Sorry?
-1 hj 0, degree 0, global section through -1.
Sorry, I didn't.
No, this j.
Yeah.
-1 to the j, if j is 0,
Yeah.
then the -1 acts trivially on constant.
Yeah.
Oh,
That's okay, right?
Yeah, sure.
Yeah.
That's fine.
Yeah. Yeah. So -1 acts by multiplying by -1 to the j on that. Yeah. So for example, if you have an action of the circle on a real vector space and -1 negates, you can check for yourself. It has to be an even dimensional vector space. Okay, you can get a lot more from this. I'm just saying this to say this discussion, which the non-formal part of the discussion was embedded in this word preserves. Okay, but other than that, we got something out of it. And this is actually pretty interesting. All right, so this action of S1 it's something which exists on each tangent space. Okay, but by this magic of Hodge theory, you can kind of upgrade that to something that's acting on the cohomology. And you can also think of this cohomology maybe of something in terms of like physical cycles on the manifold, but then it's very hard to understand what how this S1 is acting. Okay, so it really used in so it's very unclear. It is not, and in fact, it's a very deep and interesting thing related to the Hodge conjecture, how this S1 action interacts with the rational homology. Okay, it's made in some transcendental way, and it doesn't really know about this. So if you start off with the cohomology class of an actual cycle and you rotate it, who knows what it becomes. Okay, so that's a very quick summary of what goes into Hodge theory. Now I want to adapt this to, so we can adapt this story to these arithmetic locally symmetric spaces. Are there any questions before I start that? So the main, the thing which is meant to happen is exactly the same. Namely, you have some extra structures on the tangent spaces. All right, and in the end, this comes from the fact that this is some very special type of Riemannian. This has this very restricted holonomy, and you try to promote them just as you in exactly the same way as what we just discussed to extra structures on the cohomology. Okay, so there's a fairly complicated theory of this, which is part of the theory of GK cohomology. But I'm just going to try to describe it in a toy model, and then I'll tell you what happens in general. Okay, so the picture to keep in your mind is it's something analogous to a Kähler manifold. So in the toy model, I'm going to look at a case where, so I described one case of SL2 z square root 2 where the symmetric space was hyperbolic, two copies of hyperbolic plane. This is not quite complicated enough to make the point I want to. So I'll take a case where this symmetric space is a product of 3 copies and 3 copies of the the 3-dimensional hyperbolic space. It doesn't really matter. If you're not familiar with this, it's not really going to matter. Okay, the main point is this S gamma splits as a product, and I'm going to just use that. Okay, so there are such examples. There certainly are such gamma. I won't explicitly tell you, but it's easy to find such gamma. And the only thing I want to point out is the quotient. Okay, this space is some sort of product, but this is not a product. All right, when you take the quotient by this gamma, it mixes up the factors. Nonetheless, what will happen, the kind of magic of this Hodge theory, is that at the level of cohomology, this thing will feels like it's a product. Okay, because you will be able to promote some kind of local structure to a. All right, so what I'm going to just imitate what happened earlier. So here, what happens? If I take the tangent space at some point to this manifold, it splits. Okay, so locally, this space and this space are the same. Right, locally, this space and this space are the same. So this space has a global splitting. So that gives you each tangent space splits into 3 parts. Okay, which correspond to tangent vectors pointing in these 3 directions. Okay. Again, this is not a product, but somehow each tangent space at least splits. And that gives you a corresponding splitting of J-forms. Okay, so if you take J-forms, what you can do, if you take the sort of exterior power of this, it splits let's say J-forms split, let's call this omega J, they split as a sum indexed by integers A, B, and C, adding up to J of something I'll call omega ABC. And what this is, these are differential forms which kind of look like an A form on this component, and a wedge of B form on this component, and a C form on this component. Okay, so this you see, this splitting is a substitute for this S1 action, which you see in the Kähler case, and then again, just like you promoted the S1 action, you get this. And as before, now there's a fact which is not totally formal, which is that this is compatible with harmonic forms. So with harmonic forms, which means that if omega is a harmonic J form, and you write it according to this decomposition, and omega is sum of omega ABC, then each one of the components, then each omega ABC is also harmonic. Okay, so this is the analog of the fact in the Kähler case that this S1 action preserves harmonicity. And what that means is that this thing, so all these computations were with differential forms, but suddenly they transfer over to cohomology, and you get a splitting of cohomology of this manifold. HJM, this is a sum. It splits up into these components. Now, at this point, it's not sort of clear what these mean, but it has some kind of canonical splitting. Okay. Again, these if you take the cycle class, who knows what happens here? Okay, it's some kind of, this has no the way this doesn't really make it really works with differential forms rather than cycles, but you can make this decomposition. Okay. Now, are there any questions? So what do you do with this? I'll just show you enough to show it that it has some content. There's a further thing you can do. So in usual Hodge theory, so Poincare duality tells you that if you have a manifold, the dimension of the jth cohomology group and the dimension of kind of the opposite cohomology group are the same. Okay, and Hodge theory explains this, but gives you an explicit map, which is the Hodge star operator between the harmonic forms here and the harmonic forms here. Okay. In this case, you can do this Hodge exactly the same thing, but you can do it factor by factor. Okay, so there's a sort of a duality which now works on each factor separately, and it tells you that the dimension of this HABC, you can flip any of the three coordinates, 3 minus a, b, c, or you can flip the second coordinate or the third coordinate. I won't write that. Okay, so there's some kind of factor by factor Poincare duality, which you have here. And at this point, this puts, for example, very strong constraints on the Betti numbers. Okay, because there are very few free, like if you pick the dimension of one of these, a whole lot of them are determined. Okay, so if you work through this, and this implies that the dimension, you have to add a couple more tricks here, but it implies that if you write out the vector of dimensions. Okay, so this was a 9-dimensional manifold. If you write out its dimension vector, so dim h0 of x gamma, dim h1. Okay, so you write out this vector. It has to be of the following form. Okay, the Betti numbers must be, these are with real coefficients. Okay, it must look like this. Okay, because there are, well, let me just tell you, for example, where this comes from, okay? For some integer k bigger than or equal to 0. So I'll just say where this piece comes from. This thing here, there's okay, so this is, for some integer here, it's k, 3k, and k. This comes from something like the h111 part. Then this 3k comes from the 211, 121, and 112 parts, which all have the same dimension, and so on. Okay, so just the combinatorics of how you flip these back and forth forces this kind of constraint. All right, now, and in fact, you can understand these two pieces. They come from a like, what does this piece mean? It corresponds to, this decomposition corresponds to splitting the cohomology into two pieces. All right, so this piece here corresponds to the cohomology that this corresponds to harmonic forms that are actually invariant, under parallel transport. Okay, under transport. And this is sort of everything else. Okay, so this is some fairly simple example because there's this very simple structure, the tangent splay is just splitting into pieces. But it's somewhat surprising that for all of these arithmetic locally symmetric spaces, if you go through the corresponding reasoning, which is somehow much messier, the end result is not, there are sort of more pieces here, but the end result doesn't look so different. So in general, meaning for any of these arithmetic, any x gamma, and here I should really say this what I'm about to say is really true only in the compact case, and some you have to modify it in general. You always see some structure vaguely of this type. Okay, so this cohomology, it splits up as a bunch of pieces. Okay, so I'll just call it okay, you get a whole lot of pieces. The final one. The first piece here is the analog of this. It corresponds to forms that are invariant by parallel transport. The last piece, and this is also the largest piece. Okay, so it behaves just like this here. So this is it's kind of a very strange thing that the dimension vector of this piece looks like, again, some integer times a row of Pascal's triangle. Okay, so delta 1, 0, 0, 0. For some integer delta, so for some integer k bigger than or equal to 1, and some delta, which actually depends only on this symmetric space. And then there are intermediate terms which kind of show some mixture of these two behaviors in general. So I won't discuss them. But it's very surprising. In this case, you see this. So this came from the product structure. Okay, the fact that this universal cover had a product into three things. In general, this doesn't have to have a product structure, but you always see the sort of the largest piece of the cohomology has exactly the same dimensional data. Okay, so in other words, this looks like the cohomology of a product of delta, a torus, okay, a product of delta circles, and it's a little bit strange or striking that this happens for all of these spaces. So for example, by the way, for Ln, for this original problem we were talking about, this integer delta will be given by the integer part of n minus 1 over 2. Okay, I mean, it's very easy to figure out what this integer delta is. Okay, so all right, I want to say one more thing about this, and then I'll stop. The main point of next time is to try to explain in some way why where this comes from. But I want to say one more thing just to emphasize that it needs an explanation. So let's just suppose, to keep our life simple, that this integer k is 1. Okay, in other words, you see this piece of, you see just one copy of this. Are there any questions, by the way?
K could be 0.
K could be 0. Yeah, did I say, sorry, thanks. Absolutely, sorry. K could be 0. All right, so let's suppose that k is 1. All right, now there's something else which, there's an extra structure which I haven't told you about so far, which is that these, for any arithmetic group gamma, there's a large family of operators, of natural operators which act on the cohomology. And these are called Hecke operators. I'll just say very briefly where they come from. Okay, so gamma is some discrete group. Okay, this gamma is something like S ln z. Now, suppose that, so let me call an almost automorphism of gamma. It's just a term I made up. It's not a standard. But let me say almost automorphism gamma will be a finite index subgroup and another finite index subgroup and an isomorphism between these guys. Okay, so this is like an automorphism, except it's sort of only partially defined and not, but it fails to be only by finite index. Okay, if you have such a thing, it's not very hard to see. It's close enough to an automorphism that you can make a corresponding map on this cohomology. Okay, and the feature of arithmetic groups is that they have a very large number of these almost automorphisms. Groups have many such. Okay, they have many almost automorphisms that don't just come from conjugation. So these things are called Hecke operators. And all right, we have to. So these are a central concern of the theory of automorphic forms. But for now, all we need to know is that they exist. We don't need to. Now, what you can do. So if you have these extra operators that act on the cohomology, you can try to break the cohomology into eigenspaces. Okay, it's a reasonable thing to do if you have some natural. They all commute with each other, by the way. They all commute. Okay, so you can try to simplify this space by breaking it up into the kind of eigenspaces for the. And if you try to do that in this setting, something kind of strange happens, which you find that the Hecke operator, any one of these operators, acts by the same scalar on all these spaces here. Okay, so T acts by the same scalar on all. This is under this assumption. I said that k equals 1 on all of this piece of the cohomology. Okay, so this is something. So one can prove this, but it's very strange. Right? If you write down an operator and its eigenvalues are very degenerate, okay, you would in general like to have some explanation for that. Okay, so you would like an explanation to explain this degeneracy. Just in the sense that if I write down a matrix and it has a repeated, it should really never have a repeated eigenvalue unless there's some reason why. Okay, it just doesn't happen for. So I'd like to explain this by some extra symmetry of the system. All right, so the first thing is that all of these, not only Ln, but all of these arithmetic locally symmetric spaces, they have a piece in their cohomology that looks like the cohomology of a torus. And you have all these natural operators that act on the cohomology, but somehow they just act on this whole thing as if it were by a single scalar. Okay, so the goal, what one would like to do is you would like to explain this by producing some, like what would be a reasonable explanation. I'd like to produce some extra action on this cohomology, which commutes with all the Hecke operators, all the T, and it somehow explains this numerology. Okay, so I could hope to produce an action of some algebra on this cohomology where A is an exterior algebra on delta generators. Okay, so that's what we're going to talk about next time. So essentially, I have this conjecture that this exterior algebra, it has something to do with the motivic cohomology of some algebraic varieties, which I haven't explained yet, which are in the picture. And that's conjectural, but there's somehow many shadows of that picture that are unconditional that you can figure out, which convince you it must be true. Okay, so it turns out, I mean, at this point it's not clear that this should have an interesting answer, but it appears that the answer to it is very interesting because it's related to some kind of very subtle invariance of algebraic varieties. So I will talk about that next time.